So we are just revising things. So we began studying with STR, okay, that is special theory of relativity, and in this we primarily study the Lorentz transformations, and that can be given by this. Uh, Let me finish it. Okay, it is square dimensionally, and similarly, in the interval form, let's separate it. In the interval form can be written as gamma delta t minus b squared delta x. Okay, this is delta x, and the x coordinate will be given by this delta x prime will be given by delta x minus b delta t. Okay, and y prime equals to y, z prime equals to z. Okay, delta. Okay, by considering 1D motion. Okay, and x direction. And similarly, the inverse Lorentz transformation will be given or written. It will be written as just similar to this, but with a positive sign. Yeah, it's gamma delta t prime plus b by c squared delta x. Okay, applying. This is just why in the interval form there is no del in the y, because we are considering inertial motion or inertial frames where the speed of frames are always constant. Okay, there is no interval in this v. Speed of frame is always constant. Okay, that's why we do not include del in the v. This is prime coordinates. Okay, these are all prime coordinates here. Yeah, and z equals to z prime, delta y is equals to delta y prime, delta z is equals to delta z prime. And what is the difference between LT and ILT? It is just that from where you are measuring things and what you want to consider things, what is given to you. Suppose you are in S frame, okay, this is a stationary frame and this is a moving frame. Okay, this is a moving frame moving with velocity v. Okay, if you are in this frame, okay, and you want to you are doing some experiment in your frame only. Okay, so in your frame what will be given in your frame, that you will be known, these coordinates will be known, and you want to find, you want to analyze you want to analyze physics in moving frame. What will be the physics in moving frame? Okay, moving frame. Then you will use Lorentz transformations. Okay, Lorentz transformation, because you want to find the primed coordinates given that what is the unprimed coordinates are. And you can do the opposite when you are suppose any experiment is happening. Okay, this is S frame, this is S prime frame, and any experiment or event, experiment or events, any experiment or events are happening in the S prime frame. Okay, now what you know, suppose you are here only, but you know, suppose S prime, S prime things you know, and now, or say physics, you know the S prime physics or the physics in S prime. No, the physics in S prime frame, suppose, or it is given to you. Okay, in the question, then you want to, and you want to analyze the same physics. Okay, I mean the physics of same geometric object in your stationary frame. Okay, you know the physics in the moving frame. Okay, it is given to you. Suppose in the question, the physics or the things, whatever the observables are, it is given to you in the question. Now but you want to know what is the physics of the same event or the same experiment or say the same geometric object, what it is, what it will look in your as frame. Then you will use, then you will use okay, inverse Lorentz transformations. Okay, then you will use this inverse Lorentz transformations, because now you know what are the prime coordinates are and you want to calculate the unprimed things. Okay, that's it for the Lorentz transformations. Second thing, what we have done in SR, how does the velocity transform? How do velocities transform? It is like in prime coordinates. If you want to know the prime coordinates, it will be given as this. Okay, and 1 minus ux b by c squared. Okay, next in the y, see your, when moving in the x direction only, your, there is no change in the coordinates of y and z, but there will be a change in the components in of velocities in the y direction and the z direction also. Okay, so will be like, let me write it, v squared by c squared. Okay, this is ux in the unprimed coordinate system, and this will be same this previous one. Okay, here there are, sorry, this is y, this is y, and this is x. Okay, and in the y z direction, it will be 1 minus b squared by c squared, and same as the previous one, same as the y component. Okay, this is the velocity. Now you can check, you can check when your like object is moving with speed c in s frame, then it will also move with same speed, that is with same speed c in s prime frame also. Okay, you can check it from by putting ux here as c. Okay, and you will find that in all these cases you will find that in the prime coordinate also the speed of light is, or the speed of the object, say it is also c. Yes, of course you can say that light travels with speed c, but but in nature there can be other things also that can travel with the speed of light, like gravitational waves. Okay, so this is the velocity transformations. Now we have studied some cases like what is time dilation. Okay, time dilation. Okay, it is time dilation between two events, okay, that are that are co-local. Time dilation always occur when these two events are co-local in moving frame. Okay, so it is connected to co-locality of two events. And how does it, the formula or the expression look like? It is the improper time, okay, measured in the rest frame, or say the stationary frame. Improper time is equals to proper time divided by 1 minus v squared by c squared, or you can simply write it as gamma into proper time multiplied by proper time. Okay, so this is time dilation, because why it is time dilation? This is in stationary frame, and this is, we define the time in the moving frame, proper time in the moving frame. Why? Because if a clock is moving, if a clock, okay, if a clock is moving, we define such a time in its own frame, okay, as the proper time, because in its own frame the things will be valid, and as seen from different observers, time will change accordingly. Okay, the time will change according to this equation. So if I am in my frame, okay, then in the moving frame, if I have defined this time as proper, then it will be dilated, because gamma is always greater than 1, then I will get the time to be dilated, okay, to some gamma factor. Now similarly, just uh, note that this time dilation formula is only applicable when the two local when the two events are local in the moving frame. Okay, so in the previous classes we have talked about a digital clock. Okay, it was blipping on the same place, okay, in the s prime frame. In the moving frame it was blipping on at the same location. Okay, same location. Okay, we will see an example of it also. So let's finish this quickly. Okay. This is mostly a revision class. We will just briefly introduce a new topic today. Okay, so it may help you to just reconcile things. So next topic was length contraction. You just have to memorize these things, okay, for special theory of relativity. And the length contraction between two events, okay, occurs, let me write it, occurs when occurs between, yeah, length contraction occurs between two events that are simultaneous, okay, that are simultaneous in stationary frame. Okay, so this is the main points. You must note that why and when will length contraction actually happen, and when will time dilation will actually happen. And its formula can be given by improper length is equals to proper length. Okay, proper length is defined as the length of a moving object, length of a moving object in its own frame. Okay, this is same as proper length. Okay, it's proper length divided by gamma. Okay, where gamma is equals to this one by root over 1 minus v square by c square. And of course, again, gamma is always, it is always greater than 0, greater than 1. So, if it is greater than 1, this improper length will be less than the proper length. Okay, so that's why we say the length is contracted. Okay, now let's see an example of what is thing for time dilation. These are important concepts, so I'm just going through them in depth. Okay, an example of time dilation. Okay, let's take it. Imagine a hyper fast train. Okay, this is train moving rightwards. This is up rightwards, faster station platform at 50% the speed of light. Which we can call this as, we can write this as the speed of the S prime frame. Okay, S prime frame is the moving frame, that is a train, and it is traveling with a velocity that is 50% of the speed of light, that is 0.5 multiplied by c. Okay, so we can imagine this is a train. Okay, so this is a hyper fast train, and it's moving with velocity. So, okay, and there is a person sitting here. This is a chair, and there is some person sitting here. Okay, and I have a platform here. This is train, it's S prime frame. This is my platform. This is my stationary frame. Okay, and there is another observer here at rest. Okay, this is moving. This is also moving with speed. This observer, or this say this passenger, is also moving with the same velocity as the train is moving. Okay, so this passenger is at rest with respect to this train, but is at not rest state with respect to this particular observer at the platform. Okay, so case one. Let's take case one. Uh, let's suppose the events are co-local events. Co-local. Co-local. Okay, this is my case one. So let's define our event. Event one is that a passenger sitting inside a moving train snaps his fingers, these are our fingers. Okay. Snaps means just you know that what is snapping your fingers. Chutke bajana in the Hindi. So you know what is snapping your finger. So suppose this event one is that a person sitting inside a moving train snaps his fingers. Okay, and event two. Okay, again he or she snaps fingers. Okay, at same seat. Okay, this means the two events are co-local. Okay, they are happening at the same location, at same seat. Okay, again she snaps fingers at same seat. Okay, after let's say 10 seconds of event one. Okay, so event one is that he just snapped his finger, and then event two is he just again snapped his finger after 10 seconds. So these are two defined events. So in moving frame, that is my S prime frame. Okay, what will happen? My location is fixed. Okay, there is no difference in the location, but my del t prime is 10 seconds. The difference between the time between these two events is 10 seconds. So what will happen in the S frame? Hmm, what will happen, or how will the observer? Okay, how will the observer? How will the observer observe at platform see these events? Okay, so in S, that is S frame, what will happen? You know, let's because we are translating our physics from a moving frame to a stationary frame, then we must use this in inverse Lorentz transformations, because what is given to us, the coordinates of, or say the intervals of S prime frame is given to us. Now we want to calculate what is the physics in our stationary frame. So we will use the inverse Lorentz transformations. Okay, so it's gamma delta t plus v by c squared delta x prime. Okay, so of course the location is 0, the delta x is 0 because the location is fixed. So what will happen? What I will see is a dilated time. Okay, this is a This is the time dilation formula because it only happens when the two events in the moving frame are co-local. Okay, and what will happen? You can calculate that the gamma will be 1.15 at velocity is equals to 0. Okay, you know what is gamma. It is 1 by v squared by c squared. Just put the v, you will get the gamma. Now what will be that del t? It will be what will it be? I haven't calculated it, but you can calculate this. Okay, you just calculate 1 multiplied by 10 seconds. Yeah, that's easy. So it will be 11.5 seconds in the S frame. In S frame or stationary frame. Okay, so you see the time is getting dilated. So if a moving train, if a train is moving at half of the speed of light, okay, so and if he snaps his finger after 10 seconds, okay, what we will see that what we will observe the time between those two snaps is actually elongated or dilated from 10 seconds to 11.5 seconds. Okay, but what if I take a second case, non-polarized events? What will happen? Okay, now suppose event 1 is back passenger. Okay, there is a passenger behind this passenger. Now let's make another passenger here sitting here. Okay, he snapped his fingers. He will also snap his finger. Now back passenger snaps his finger. Here's your third finger. Okay, that is my first event, and my second event is front passenger. Okay, sitting at 1 meter, so it's 1 meter ahead ahead of back passenger. I think the spelling is wrong. Passenger should be ES. Okay, back passenger. After again 10 seconds. Okay, so first of all, the back passenger snaps his finger, and then after 10 seconds, the front passenger will snap his fingers. Okay, and the distance between both is 1 meter. Okay, it is. So the two events are not co-local. Okay, now the events are non-co-local. So what will be? So we will not use this kind of time dilation formula. Still, the time dilation will occur, but what will happen now? We have to analyze using the full inverse Lorentz transformation equation. What it is? That is delta t is equals to gamma delta t prime plus v by c squared and delta x prime. Right? Of course, we have calculated at such speeds the gamma is 1.15 and delta t prime is 10 seconds. Okay, and what will happen to v by c squared? Let's see, this is my v and this is c squared. and they are separated by 1 meters, right? What will happen? Delta t will be calculated as this is 11.5 seconds plus we will get something kind of 0.5 divided by c seconds. Okay, this is the time you will get. So of course the time is getting dilated, but it is also getting dilated, not dilated, yes, it is also getting contribution from the motion of the uh, this system, this flow co-local. I mean, they are not co-local. So due to the motion, okay, due to the motion, the information will take a bit of more time to reach you at the platform. Okay, so it will get a bit of more time than the previous time now. So time is dilated more in this case, but this is not actually the time dilation. Time dilation is only known by this formula. Okay, this is the proper formula of time dilation, and it only occurs only occurs when the two events are co-local in one frame, in one moving frame. Sorry, that's this moving frame. Why I'm saying that this is only the time dilation, it is also happening in this direction, in this case, because it may happen that this can be reduced. I mean, this can be in negative direction. Okay, you can have a negative value here, and then you will see that time dilation is not actually getting more dilated, but less dilated. Okay, so this is the standard time dilation thing. Okay, this is the standard time dilation, and the same thing will happen. And the same thing will happen for length contraction. Same thing happens for length contraction. Okay, it only happens for simultaneous events in stationary frame, measured in stationary frame, because we know that whenever we want to measure the length of any moving rod, we will do that is simultaneously. If you don't do that simultaneously, this length contraction will get somehow the contribution from like the motion of the moving frame itself, moving rod itself, and it will take more time or less time, it will be disturbed. Okay, it will be like, it will be some effective length contraction kind of. Okay, so the standard length contraction occurs is defined at when the two events are simultaneous in the stationary frame. Okay, that's how the thing is. You can see the same thing, similar thing, the length contraction also. So let's move forward. If you have any question, you can ask to me. Okay. So when we have studied about what are space-time diagrams, like space-time diagram, okay. Just wait a second. Okay. Let's do it fast. We have seen that how to make these kind of graphs, and the space-time graph is between the time axis and the space axis. Suppose it is r axis, okay, and it contains all the x, y, z coordinates. Okay, so how will it in this S frame? Why I'm calling it as S frame? Because I'm taking the coordinates as the unprimed coordinates, and I want to see how will the primed axis will look like. And we have done this in the previous class. You can check previous videos. Okay, so these are my primed axis. Okay, these are my primed axis. It will look like this, and you can find the equation of this simply. Now just take suppose three events here like this. Okay, this is my A event, this is my B event, okay, and this is my C event. Suppose. Okay, let's draw kind of this. Okay, you can again take this and you can on this. You can define here. This is suppose R1. This is R2. Okay, this will be CT1. This is CT2. Okay, and okay, how will you analyze the same events in this primed frame? You can analyze this by a parallelogram method. Okay, so you just what you will do that you are doing uh, just as in the S prime in the S frame, you are just drawing these dashed lines parallel to the axis. You have to draw the dashed lines parallel to the primed axis. Okay, and you will get a parallelogram kind of thing. Okay, let me take another. Okay, so first of all, let's make it yellow. Okay, this is my primed frame. Okay, let's take it precisely. This. So when you want to trace your coordinates, you just have to make a parallel to the r prime coordinates. You can just make like a parallel thing to this. Okay, and similarly a parallel line this one. Let's take this t1 prime. Let's take this ct2 prime. This is ct3 prime. Okay, similarly you can draw, yeah, sorry, not like this, but I have to make a parallelogram. Now it should be parallel to t prime axis. Okay, so you can draw like this, you can draw like this, and you can draw like this. Okay, these are my three coordinates in the prime. So this is r1 prime, this is r2 prime, this is r3 prime. Okay, so this is how you trace your coordinates in the prime coordinates in the space-time diagram. Okay, by a parallelogram method. Now you see that in S frame, sorry, so in S frame, okay, B and C are simultaneous events. Okay, but not, but okay, what is an event here? How can you trace it? Every point, any point you take in this graph is an event. Okay, any point. This A, B, C, all are events. So B and C, B and C, okay, are, like, you can extend it. Okay, B and C are simultaneous because they are occurring on same time, that is T1. Okay, events in the S frame, but they are not non-collocal. Why? Because you can see, you can trace it that they are happening at two different places, that is R1 and R2. Similarly, you can see that A and B are co-local, but not simultaneous. Okay, they are not simultaneous in S frame. A and B, okay, they are happening at two different times, but at same location. That is R1. That is R1. They are happening at same location. That is R1, A and B, but they are happening at different locations in the time axis. Okay, that is means different times. And now see, in S prime frame, what about B and C? Let's analyze B and C. Okay, they are happening at different places, of course, R1, R2 prime and R3 prime, and they are also happening at different times, T2 and T1 prime and T2 prime. So B and C are neither simultaneous or nor co-local. Okay. They are neither simultaneous nor co-local in S prime frame. Analyze A and B. What will happen? They are co-local in this S frame, but what about in S prime frame? They are also non-co-local and non-simultaneous. Again, A and B are neither simultaneous nor co-local. Okay, so in such kind of diagrams, you can just check that whether the events will be co-local or non-co-local in moving frame or stationary frame. Okay, this is how you check it, and we have checked it. We have seen from the Desmos also how these transform actually. These axes do transform as we increase our speed of S prime frame. Okay, let's move forward. Then we have what we have learned about is space-time interval kind of things, and it is most fundamental thing, space-time interval, also denoted as ds. Okay, you can write it as ds prime, ds squared also, because it is more convenient. Okay. ds squared is given by minus c squared by d squared plus del x squared plus del y squared plus del z squared, or you can write it simply as del x or del r vector. Okay, or even if you not write the mode, it's fine. It should be squared because it is squared, so those vectors should be multiplied with a dot product. Okay, so they are the sorry the space-time interval is an Lorentz invariant quantity. Okay, Lorentz invariant quantity, just like mass. Okay, it is a Lorentz invariant quantity. Just like speed of light, it is also a Lorentz invariant quantity. Okay, so constancy of speed of light actually tells us that del s prime is equals to del s square. This is invariance. Okay, so then we have analyzed a cone of light. Okay, that there should be a cone it is at theta equals to 45 degree. All the particles that are traveling with the speed of light, okay, are traveling on this cone surface. Okay, this is a conical surface. So we can just write it like this is a light like, we call it light like conical surface. Okay, and what are the properties of this? Here, what happens is del S squared is 0. Okay, or say your c squared del t squared is equals to del r squared. Okay, or you can say that c is equals to v, or say v equals to c. The speed of, sorry, the speed of any object, okay, is c on this conical surface. Then we have seen that here this is interior of the light cone. Okay, this is the interior of the light cone, and we call it like time like region. Okay, time like separated event. The two events in this region are called like time like separated events. Okay, so here the del S squared is negative, means this will be positive, I mean not positive, greater than delta squared. Okay, or you can say that the speed is less than c. Okay, you just take this c, that delta t squared here, you will find that that is v. You define your delta r by delta t as v, and you just can calculate it from here or derive it. Okay, and similarly you can, this is my whole space, this is whole space, this outside space is space like region. Okay, and it is given by this, or say my, it is less than, or the space part is greater than time part, and you can write it as like this also. Here the particles move at greater than the speed of light. Okay, so this is the light cone, and it helps us to read the code. It helps us, such diagrams, such light cone helps us clearly. Such light cone diagrams helps us, help us analyze the causal structure, the causal structure of space-time. What do we mean by causal structure? We have a causality. Okay, we have some causality. Okay, that whether effect will happen after the cause or not. Okay, so in this time-like region, and time-like region, the ordering is followed. Okay, say it is invariant quantity, but in space-like region, ordering is not followed. Okay, not invariant. Okay, let's take an example of a space-like thing. Okay, let's take a simple example. That is, suppose there is an observer. Right? There is an observer. Okay, in S frame. Okay, its coordinates are given by, and there are two events. Event 1 is given as 2 seconds, comma 2 light seconds. Okay, and event 2 is given by TB XB equals to 3 seconds and 5 light seconds. Suppose this is how I define my events in the S frame. Okay, now you can see, note that TB is greater than TA. Okay, now you can calculate some space-time invariant quantity, that is space-time interval quantity, that is this delta x squared, and it can be given by 1 light second by 1 light second because it is a distance. Okay, light second is also a distance. And what is this is the delta t. Okay, delta t means the difference between both, and it is 1 second. The difference between both is 1 second. When you multiply it with the factor c, that is the magnitude c, you can call it as 1 light second. Okay, so 1 light second, the speed travels 3 into 10 to the power 8 approximately meters, and that is called the 1 light second distance. Okay, this is squared and 3 light second squares. Okay, so here also this is the unit of distance, and it will be 8 light seconds, right? And it is greater than 0. So this means if it is greater than 0, this is space-like. Events are space-like separated. Space-like separated. Okay, and in space-like separated events, in the space-like region, I have told you that ordering is not followed. Ordering is not followed. Let's check it. Okay, let's check it quickly. That suppose my S prime frame. Okay, the relative speed v is c by 2, means my gamma will be 2 by 3. Okay, when you calculate it, and beta, okay, which is v by c, of course 1 by 2. Okay, now you see, apply the Lorentz transformations. You apply your Lorentz transformations. Okay, you have to do this. What you will get is that c delta, sorry, c t dash t prime will be 2 light seconds. Okay, and this prime, this will be this light seconds. Okay, singular happening will be this much. Okay, let's write it. Okay, let me write it like this. Okay, and x prime b for b event is this much. Okay, so what do you notice here is that the coordinates event 1 E1 is defined in S prime frame. Okay, in S prime frame E1 is defined by the coordinates equals to seconds and 2 by 3 light seconds. Okay, and which is roughly equals to 1.15 seconds, and this is roughly equals to this light seconds. And if we talk about event 2, it will be x. Of course, you can write it like this, like seconds. And when you calculate it precisely, give it seconds or 4.04 light seconds. Okay, so you see what did you notice here, that t a prime is greater than b prime, but we have seen that this was less than this in unprimed coordinates. Okay. This is S prime frame and this is S frame. Okay, where it is S frame, we have calculated it. Here you can see that TB is greater than TA. Okay, TB is greater than T in S frame, but the ordering has changed. Ordering is changed. In space like separated events. So causality is actually broken. Causality is broken in such region. Why? Because the primary reason is that the speed of any object can travel more than the speed of light in such regions. Okay, so it breaks the causality. It breaks the ordering of time and event times. Okay. Wait a second. Okay, I will just take a few more seconds to introduce a new concept. Okay, then we will finish our class. Okay. So from this class, we will study the structure of space-time, because we have now seen that how space and time are connected by the Lorentz transformations. The time is not independently flowing in our universe, but it is connected to how you are located, how the events are located in this universe, where are they located. Okay, and you can see this, of course, from the Lorentz transformation equations in the interval form also. Okay, so we will study the structure of a space-time now, and for it we will require some notions. Okay, structure of space-time. The first notion, some notions. The first notion is metric. Okay, what it is metric, and let's see what is metric space. Okay, so let's define it in mathematics. In mathematics, okay, a metric space is a set together with a notion of distance, okay, between its elements. Okay, usually we call them points. usually called points. Okay, the distance is measured by a function. If the distance is measured by a function, we call as a metric function, or say metric or distance function. It is a function. Okay, the distance between any two points or any two events will be measured by something, some mathematical thing. We call it metric. Okay, and this metric is actually a metric function. Okay, this is a function of something. So formally, you can write it as formally a metric space given by some. It is a metric space denoted by x and a distance function, that is d. D is a distance function. Is a set. Okay, this is sky with a metric. Okay, function with a metric function d, okay, defined on chi. Okay, and such that is d is a function such that it takes a value in this chi matrix, take its Cartesian product, and it will lead to some value between this 0 to infinity. Okay, this is closed interval, this is open. So this is a mixed interval satisfying satisfying okay, satisfying the following expressions. Okay, for all points A, comma B belonging to the sky. Okay, and what are these? So the first example is that the distance from a point to itself is 0. It is 0. So it can be denoted as t from A to A. Okay, is 0 because and the A belongs to this sky. That is our metric space. Secondly, the distance between two points is always positive. Always positive. Positive definition is also called positivity of metric. It is always equals to 0. Third one is the distance, okay, from A to B is always same as distance from B to A. Okay, also called as symmetry. Symmetricity or symmetry. This is positivity. Okay, positivity. You can say this. What you can say? An identity. some kind of this I don't know. Okay, so the symmetry is like from A to B is equals to from B to A. Okay, and the fourth one, the last one, is the triangle inequality. Inequality. Okay, it holds like the distance from A to C is always less than equals to the distance from A to B plus the distance from B to C. Okay, and this is usual triangular inequality. You can see that there are 3 points. Okay, this is my A point, this is my B point, this is my C point, and if you add this distance plus this distance, so this should be greater than this CA distance. Okay, so let's see some examples and then we will finish this class. Okay, let's quickly do this. So first example is Manhattan space. This is a metric space. Okay, remember this is a metric space and we denote it by L1. Okay, and it is a space, that is, it is a real space that is denoted by R to the power n cubed. It is not actually the power. Okay, this is like dimension. So cubed with function, okay, and the function is d1 r cross r n. Okay, from to this, and it can be given precisely d1 a to b as mod of a minus b. Okay, and it is equals to summation 1 n a, or say this should be a mod mod minus ai minus pi. This is the thing. And second example is Euclidean space, Euclidean metric space. L square. Okay, it is again a real space. Cubed with just I'm about to finish. Okay, these are just definitions. You need to know these are the examples of metric spaces. Okay, and then we can talk about what kind of metric space should be considered to represent our space-time in the spatial theory of relativity. So we are just writing some examples. So real space R to N is equipped with Euclidean metric. Okay, DAB defined as AB is equals to again the mod given by I to N. This is the usual definition or the usual Pythagoras theorem, you can call it. Okay, we study in the Euclidean space, but there are different metric spaces. Okay, suppose this is my more generalized LP space. Okay, this is my more generalized metric space. is also a real space, okay, equipped with the distance function that is uh, that it has from R n to, okay, and this can be given by precisely as this is 1, this is n from I to vi, okay, and it has power p, and the square root has now converted generalized to this 1 over p root, okay. Another last example, okay, is the supremum space. Okay. It is again a real space equipped with distance function that is d infinity cross r from 0 to infinity, okay, and it is given to the dx is s. So from 1 to n mod ai minus bi. Okay, so these are some few examples, and we are now finishing this class. That is, one can easily check now, check that these all examples of distance function, distance function, okay, or say the elements of a metric space. Okay, these are the element of metric space. We generally call them matrix. Okay, follow all above axioms. Okay, so this is the thing. We end this class here. Okay. So you can see that these are metrics, and we will see why I have defined the metric space here, because to study special theory of relativity, or say the general theory of relativity, this has to be defined properly. Okay, and without metric we cannot define the notion of distance in the theory. Okay, so this is the thing mathematically. So let's finish this. Okay, thank you.